Hi everyone, I hope you're doing well. I'm going to show you your next lesson. We're going to continue our exploration of real numbers, and we're going to discuss and look at some exponents and radicals. All right, so let's get started. So to review a little bit, let's start with exponents, and notice I put my title up here in the corner of the paper, again, so that I can look back and find this easily if I need to refer back to it later on. Exponents have two components to it. You can write them like this. You can write them as some number, let's just call it A, and then they have a power up here in the top. We can call that X. This part of the number we call the base, and this part of the number up here we call the exponent. So we're going to be looking at numbers that have an exponent written up above them like that. So let's take an example. We'll start with a very common example. Let's see, these are exponents. Let's say we had 3 to the power of 5. That's the way we'd read it, is 3 to the power of 5. 3 is the base, the exponent is a 5. Now a common mistake is just to calculate that as 3 times 5 equals 15. That's not the case. What this really means is 3 times itself 5 times. Hopefully that's review for you. Now, here's the extra challenge for today, and the challenge has a meaning behind it, which you'll understand a little bit later. The challenge is we're not using any calculators today. You're not allowed calculators on these notes. You're not allowed calculators on the homework, even just to check. I want you to do no calculators today. We're going to be relying on our brain power to solve these. So you can write an exponent in an expanded form like this, and then I can use that to help me solve it. I can break down the multiplication into its different components like this. So 3 times 3 is 9. I bring down the multiplication symbol. 3 times 3 is 9. And then I bring down the multiplication times 3. Okay, 9 times 9 is 81. So all I need to do is 81 times 3. And I can do some mental math, or I can write it out. 1 times 3 is 3, and 8 times 3 is 24. So 243. That's what 3 to the power of 5 is equal to. It's not equal to 15, it's equal to 3. Rather, it's equal to 243. Now, all the different problems you see will work just like that. It works with decimals too. Let's say we had a rational number that wasn't an integer, or wasn't a whole number, or wasn't a natural number, it was just rational, like 1.2. Well, if we had 1.2, let's say, to the power of 2, you could also read that as 1.2 squared, or 1 2/10 squared. So it's really helpful to write it out in the expanded form, like this. You don't always have to, though. So I'm doing 1.2 times itself. I'm tempted to just say it's 2.4, but that's not going to be the case. For this one, I think I'm going to do some multiplication longhand. So I like to stack them. 1.2 times 1.2. And if you remember about how to multiply decimals, is at first, you just ignore the decimals. I'm just going to do some multiplication. So 2 times 2 is 4. 2 times 1 is 2. And then I've put my placeholder in. I like to write it like this, my 0. And then I do the tenths over the tens column over, actually it's the ones column, since it's a decimal. 1 times 2 is 2. 1 times 1 is 1. And then I add together my results, and I get 4, 4, 1. Now, because we were multiplying decimals, I have to count where to put my decimal. This had 1 digit behind the decimal. This had 1 digit. So if we put those together, I should have 2 digits behind my decimal. So my answer is 1.44. And I like to box my answers. You should box your answers as well. This was our answer to the first one. This is our answer to 1.2 squared. It's 1.44. Interesting. A rational times a rational gave us another rational. I wonder if that's always going to be the case. There's one more type of exponent I want us to look at, and that is, what if we have a fraction? Let's say we had 2/4. I just realized now that's an unsimplified fraction. It doesn't matter. Let's say we have 2/4 to the power of 3. Okay, well, think of it as 2/4 times 2/4 times 2/4. And how do you multiply fractions? You just multiply straight across. Numerator times numerator times numerator, and all the denominators multiplied by each other. So 2 times 2 is 4. 4 times 2 is 8. I'm going to have an 8 on top. 4 times 4 is 16. 16 times 4, let me think for a minute. 16 times 4, that's going to be 24, and then the 4 out there, so that's going to be 64. I get 8 64ths, but we want to always simplify our answer unless there was some reason that we didn't want it simplified. If we don't have any directions, then we're going to simplify it. I know that 8 can divide evenly into both the top and the bottom. So when I divide that, I get 1/8. Interesting. 2/4 to the power of 3 is 1/8, or another way to think about it is 1/2 to the power of 3 is 1/8. So when you multiply a fraction like this continually, you get a smaller number. Okay, good patterns to know. These are all exponents. Let's talk a little bit about radicals. So let's see, I will title this radicals. The radical is the name for this symbol right here. Okay, and usually it's a square root symbol. Sometimes it can look like other things. Later this year, you'll see radicals that look like this, or maybe they look like this. Maybe that's new to you. If so, hold on, you'll learn these later this year. But all radicals act the same. They all act like a square root. So let's talk a little bit about how these work and what we get. There's two kinds that we need to deal with right now. And we're going to be looking at the two kinds of square roots. I'm trying to think about how I want to organize my notes. You know what? I think I want to add some highlighting. Yeah. Here were my exponents. Here are the radicals. And let's take a look at the square roots. Now, we could see something like this. Let's say, let me just create a list of some square roots over here. These are going to have some common features here. Let's talk about the square root of 0, the square root of 1. I'm going to skip a little bit, the square root of 4, and let's do the square root of 9. This means what times itself, that's what that square root symbol means, that radical. What times itself makes 0? Well, 0 times itself is 0. So we'd say the square root of 0 is 0. This is asking what times itself makes 1. That's 1. What times itself makes 4? Well, 2. 2 times 2 is 4. And you can see the patterns going 0, 1, 2. This one's probably going to be a 3. 3 times 3 is 9. Okay? So square roots work like that. They're kind of like backwards exponents. What I would do is I'd give this an exponent of 2 to make the number inside. Here I'd give this an exponent of 2 to make the number inside. That's why we're looking at radicals and exponents together here. Since all of my answers simplify to a whole number, actually it simplifies to an integer, whole number, all of them are natural except for this one. These are what we call perfect squares. We love perfect squares because it comes out to a nice number like that. That's not always the case. Actually, that doesn't happen very often. Over here, we skipped the number 2. I wonder what we would get if we did the square root of 2. We also skipped 3. I wonder what we would get if we did the square root of 3. We did square root of 4. What about the square root of 5? Or we'll do one more, the square root of 6. Now, if you remember from our lesson before, the square root of 2 is an irrational number. It's a decimal number that goes on forever. It doesn't repeat. There's no pattern to it. It just continues on forever. Now, I could use a calculator to figure it out, but today we're not using calculators. So instead, I need to rely on another method, and what I'm going to do is I'm going to estimate. And what I want to do is I want to figure out my estimation for these other kinds of square roots, the ones that aren't perfect squares. And you know what? I might even highlight square roots here. Okay, well, is the square root of 2 going to be, where is it going to be? That's what I'm trying to think of. Well, the square root of 1 was 1, and the square root of 4 was 2. And the square root of 2 is in between the 1 and the 4. So my estimation would be something between 1 and 2. It'd probably be like maybe like 1.3, maybe a little bit closer to the 1 than the 2, maybe 1.2. I don't know, but what I'm going to say is I'm going to say that this answer is between the integers 1 and 2. That's my best guess, my estimate. I think the square root of 3 is also going to be between 1 and 2. I think it's going to be close to 2. Maybe it's going to be like 1.8 or something. So my estimation for this would be between the integers 1 and 2 again. Now, I think this number is going to be larger than this number just because the number inside the square root is going up. Now, let's see, the square root of 5, it's going to be more than 2 because the square root of 4 was 2. It's going to be less than 3. So I would say this is probably between 2 and 3. My paper moved on me. And the square root of 6 is also going to be in between 2 and 3. Between 2 and 3. Hopefully you see a nice pattern going on here. If these irrational numbers are in between perfect squares, then you know where the number is going to land around. You can say, you can estimate which integers your answer is going to fall between. Now we can check it with our calculator. Let's see what we get. To use the square root, I have to hit, I'm looking for that square root symbol, which is right here, but it's in yellow. So I turn on my calculator on, and then to get that yellow option, I have to press second, and then that button. There's my square root. So the square root of 2 is 1.4. It is between 1 and 2. Great, our estimation is awesome. The square root of 3 is 1.7. Again, it worked. When you're doing your work today, don't use a calculator. I'm just showing you that our strategy is working and it will continue to work. Okay, by using perfect squares, you can estimate the square roots without a calculator. The square root of 5 should be between 2 and 3. It is. And the square root of 6 is also. And the numbers are getting up as the number inside the square root grows. Awesome. Okay, so that's how you can calculate the radical or the square root of a number without using a calculator. Now, inside we had all these really nice numbers. What if we didn't? Let's look at an example with maybe, let's say, a fraction in there. I'm running out of room. I think I can fit it in here though. And you know what I'll do? Yeah, I'm just gonna do it right here. Let's take the square root of fractions. Square root of fractions. And I'll highlight that. That's gonna be our next piece. Let's say we want to take the square root of 9/16. You could use a calculator, or there's this really neat pattern that shows up with square roots. When you're taking the square root of a fraction, there's an equivalent operation you can do that's going to give you the same answer. You can take this, I think of it like this. You can take the square root symbol, the radical sign, and you can share it and distribute it between the 9 and the 16. So instead of writing it like this, I can write it like this, And this gives you the same answer as this. This means what number times itself makes 9/16. Actually, maybe you can already think about that in your head. I just thought of it as I was reading it. But if you can't think of it right away, well, then rewrite it. Do you know the square root of 9? Sure, that's 3. And what's the square root of 16? 4. Hey, look at that. What times itself makes 9/16? 3/4. Awesome. So when you're dealing with fractions, if you can't do the mental math, you can instead break it into numerator and denominator and do the square root of both of those. Okay? Let's do another one. The square root of 1/36. What number times itself makes 1/36? Well, let's rewrite it as the square root of 1 over the square root of 36. Well, what times itself makes 1? 1. What times itself makes 36? 6. So the answer is 1/6. And I think you could even change that to a decimal if you wanted to for some reason. But I don't think you need to. Okay. All right. So today we expanded our understanding of real numbers, and we looked more specifically at exponents and radicals, and not all the radicals, but just the square roots and how those play into some of our calculation. And we used integers, we used whole numbers, natural numbers, zeros, rationals. We used irrationals, and what we did with the irrationals is we've just done an estimation with images. Okay, so that's it for our lesson. Let me tell you your assignment, and I'll also post the assignment in Schoology as well. Okay, just like before, you can continue on your paper. I'm out of room now, so I'm flipping it over. We're going to break this up into 2 different pieces. First, I would like you to do, we're going to do page 13. We're going to do numbers 11 to 14 and number 16. You know what, with all of this work today, no calculators, not even on the homework, not even to check. Don't even use them to check. Just rely on the patterns that I showed you there. We're also going to do some from the other page. We're also going to do page 20. Again, no calculators. We already did some on page 20. This time we're going to do numbers 13 to 15 and 19 to 22. Now, I'm changing the directions a little bit on you. When you read the directions for page 20, it tells you to round, no rounding. In none of the work I showed you in those examples did we ever round. Instead, what you're going to do is you're going to estimate with integers. For example, on the front, what did we say? We said the square root of 2. This will be an example. I'll put EX. The square root of 2. In the book, it tells you, it might give you square root of 2, and it says round it and give an estimation. We're not rounding. Instead, you would just say the square root of 2 is between, what was it between? It was between 1 and 2. That's what you're going to be doing for the problems on page 20. Okay? All right. Good luck. See you next time.